Another day, another story. Nearly everything we know about the universe comes from electromagnetic radiation, that is, light. Astronomy began with visible light and then expanded to the rest of the electromagnetic spectrum. By using the spectrum from the short wavelengths of gamma rays to the long wavelengths of radio waves, astronomers have discovered strange and wondrous things. Now a new form of astronomy, gravitational wave astronomy, has come. Welcome to Tabo Eminent Channel. It watches not light, but movements in space-time. Along with the new astronomy has come a new kind of observatory, the Laser Interferometer Gravitational-Wave Observatory, LIGO. Gravitational waves are ripples in space-time. According to Albert Einstein's theory of general relativity, gravity is not a force reaching out through the universe. It's a bending of space-time. When an object accelerates, it distorts the space-time around it, and that distortion travels away from the source at the speed of light. Gravitational waves are ripples in the fabric of space-time itself, caused by the acceleration of massive objects. According to Einstein's theory of general relativity, massive objects like stars and black holes warp the space-time around them. When these objects accelerate or change speed, they create waves in space-time that propagate outward at the speed of light. These waves carry information about the mass, velocity, and gravitational interactions of the objects that created them. Gravitational wave detection has opened up a new window for astronomers to study the universe, allowing them to observe phenomena that were previously invisible. Gravitational waves come from really heavy objects. So how massive an object are we talking about? The first proof that gravitational waves actually exist came from a binary pulsar, two neutron stars, each about the mass of the Sun, that orbit each other. The pulsar's orbit is gradually shrinking, so the pulsars are losing energy. That energy is exactly the amount that general relativity predicts that the pulsars would give off in gravitational waves. When two black holes orbit each other, they emit gravitational waves as they accelerate due to their immense gravitational attraction. As they spiral inward and eventually merge, they release a burst of gravitational waves. Similar to binary black holes, binary neutron star systems emit gravitational waves as the neutron stars orbit each other. When they finally merge, they also produce detectable gravitational wave signals. These are systems where a black hole and a neutron star are in orbit around each other. As with binary black holes and neutron stars, their orbital motion generates gravitational waves. The violent explosions of massive stars during supernovae can create asymmetries in the distribution of mass and energy, leading to the emission of gravitational waves. The effect of gravitational waves is very, very small. Since gravitational waves are a ripple in space-time, they cause the distance between 2 points to change ever so slightly. How slightly? LIGO must be able to measure distances as small as 1019 meter. The proton has a radius of about 0.85x 1015 meter, or 10,000 times larger. Gravitational waves have an incredibly tiny effect, especially when compared to other fundamental forces like electromagnetism or the strong and weak nuclear forces. This is because gravity itself is a relatively weak force, and gravitational waves are even weaker perturbations of that force. The effect of gravitational waves on objects is described by the concept of strain, which quantifies the amount by which distances change due to the passing gravitational wave. However, this strain is typically extremely small. For example, the gravitational waves detected by the Laser Interferometer Gravitational-Wave Observatory, LIGO, and Virgo collaborations involve strains on the order of 10^21 or smaller. This means that gravitational waves cause changes in the lengths of objects that are on the order of a fraction of the diameter of a proton. Despite their tiny effect, the detection of gravitational waves has been a monumental achievement in physics and astronomy, as it opens up a whole new way of observing the universe and provides valuable insights into some of its most extreme and mysterious phenomena. Measuring gravitational waves is tricky. To detect a change in distance much smaller than the proton requires great precision. Each LIGO installation is a laser interferometer made up of 2 underground pipes, each 1.3 meters, 4.3 feet wide, and 4 km, 2.5 miles long, set in an L shape. The inside of the pipes is a vacuum. When a gravitational wave passes through LIGO, one arm of the instrument gets longer and the other gets shorter. A laser beam is split in half, sent down the 2 pipes, reflected back, and then recombined, so the 2 beams cancel each other out in destructive interference if there is no gravitational wave. If there is a gravitational wave, the beams won't cancel each other out. A 4 km long beam is still not enough to detect a gravitational wave, so the beams are bounced back and forth about 400 times, so the light travels a distance of 1,600 km, 1,000 miles. Gravitational waves cause extremely small distortions in space-time, making them incredibly difficult to detect. Instruments capable of measuring such minute changes must be incredibly precise. Gravitational wave detectors are susceptible to various sources of noise and interference, including seismic activity, thermal fluctuations, and even quantum fluctuations. Distinguishing the signal from the noise requires sophisticated signal processing techniques. Gravitational waves propagate at the speed of light and weaken as they travel, making their detection even more challenging. Detecting waves from distant cosmic events requires sensitive instruments capable of measuring extremely subtle effects. The detectors used to measure gravitational waves, such as LIGO and Virgo, are among the most complex scientific instruments ever built. They involve multiple kilometers of ultra-high vacuum tunnels with laser interferometers that must be precisely calibrated and maintained. Once a signal is detected, it must be independently verified to ensure that it is indeed a gravitational wave and not the result of instrumental artifacts or other sources of noise. LIGO is very sensitive. LIGO detects such a small change in distance that it can detect a lot of other vibrations too. For example, the speed limit at LIGO is 16 km, 10 miles per hour, to minimize vibrations from nearby cars. One source of noise is gravity gradient noise, which is the minute change in Earth's gravitational field when a vibration passes through the ground near the mirrors. The mirrors that reflect the light weigh 40 kilo, 88 pounds, and hang by silica fibers in a complex suspension system. To make sure that LIGO does detect gravitational waves and not just passing cars, there are 2 LIGO installations, one in Livingston, Louisiana, and the other in Hanford, Washington. A gravitational wave would show up at both installations. Gravitational wave astronomy can see an entirely new side of the universe. If supermassive black holes 1 million times more massive than the Sun, merged in a distant galaxy, LIGO could observe it. Scientists also expect that if a neutron star is slightly non-spherical, The gravitational waves could be observed and thus reveal much about the star's structure. Every time astronomers have been able to look at the universe in a new way, they've always observed something unexpected, and gravitational wave astronomy will likely show something not yet thought of. Thanks for watching. Request you to subscribe the channel.